Welcome back to Grad Stats, University of Cincinnati. This is video lecture 6, the last one for this week. So this is the last piece where I will continue to explore and make us think a little bit about the data and how once you have a data set with a set of observations, that new questions can be asked about it. For example, what factors might have contributed to the increase in life expectancy that we have observed, the 40 years of increase in life expectancy? So we could raise as a possible explanatory variable, make a theory, that fertility rate, changes in fertility rate might be driving or explaining the changes in life expectancy. So the outcome variable in this scenario would be life expectancy, because that's the thing we want to explain. What's the theory here? Well, here's the theory. Stress increases in proportion to the number of children that a person has. And stress leads to health issues. So I'm beginning with these two premises. Then the logical conclusion is that a decrease in fertility rate might explain an increase in life expectancy. Now, note that this is a made-up theory, perhaps inspired by quarantining with a 7-year-old and having to work and help her learn remotely herself at home. Anyhow, the important thing is that it is a testable hypothesis with data. The thing we need to know, however, is that if this theory is correct, one thing should be true. There should be a correlation, a relationship between life expectancy and fertility rate, and a special one. The relationship would be an inverse one, because life expectancy would be expected to increase when fertility rates decreases, right? You would expect to see higher life expectancy in countries that also have lower fertility rate. That would be the expected correlation if this theory is true. Now, let's take a moment to explore what types of relationships there are, because I said something funky here, an inverse relationship. So first, the relationship can be positive or direct, or negative and inverse. Positive relationships means when one variable grows in magnitude, the other also grows. When one variable reduces in magnitude, the other variable also reduces in magnitude. That's why I said that in the case of my theory, a negative relationship should be expected, because I would expect countries with higher life expectancy to have a lower fertility rate. That's an example of a negative relationship. The shape, you could have a linear or a curved relationship. And there's something else to say about relationships, about the strength of the relationship. When the relationship is strong, all data points are really coupled and tightly together around the trend that we are expressing. If it's a linear shape of the relationship, all the data points are very close to that line. And if the relationship is weak, you still might put a line in there, but all of the points are kind of far away. And then you have situations where you have outliers. And this is the case of this graph here, where you have a very tight relationship for a set of the data, for a subset of the data, but then there are clearly things that are out of range, right? Some particular units of observation is just not following the typical expected relationship. And we'll see when we look at correlations, examples of when this type of thing can happen, what it might mean. But for now, I just want to generally describe the types of relationships that exist. Now, back to our theory. If our theory is correct again, the direction of the relationship should be negative, as I said, and hopefully strong to moderate. If it's something like this, it's less convincing, right? Okay. Correlation between fertility rate and life expectancy. So here's the data. I have fertility rate and I have life expectancy for the various countries in the year 2000. And this is what it looks like. Actually, I got the data for both the year 2000 and the 1900s, both. Just put everything together. And what you see is a relationship that looks more or less like this. And it's replicated within each year as well. So it really looks like you have a moderate, it's not super, super tight in the middle. It's tighter at the ends, which makes me think here's the cluster of countries in the 2000. This is the cluster of countries in the 1900. But in general, you do see that relationship that is a bit, it's not super tight around the line, but it's also not, it's elongated. It's sort of an elliptical shape. It doesn't look like a circle, meaning that things are equally spread around the line. So there seems to be a correlation between the two. Of course, it requires inferential statistics for us to determine if this is statistically reliable. But we can, the data looks promising, let's say. And again, when you're doing scatter plots like this, you have the explanatory, what you're calling the explanatory variable in the x-axis, and what your response variable is on the y-axis. So we describe the relationship, and what I want to ask you and discuss a little bit is the title of the plot. Imagine this plot showed up at Times Magazine saying that fertility rate impacts life expectancy, and then it shows like this graph, and it discusses how countries with higher fertility rates have lower life expectancy. So it must be the case that we need to do fertility control to promote life, longer lives, blah, blah, blah. How would you feel about that? Critically evaluate this. Thus, this data, understanding that this is an observational study where life expectancy and fertility rate were measured at the same time point. We didn't manipulate any variables. We didn't mess with the data in any way. It wasn't an experiment. Can we really is the statement, the conclusion at the top of the graph, that's giving the title to the graph, is it really the story that the data is telling? Can the data, being what it is, tell that story? Take a minute to think, pause, and come back to hear the answer. So we're starting with the question, what factors might have contributed to the increase in life expectancy? And we have as explanatory variable the fertility rate. And I told you that my theory was that stress increases in proportion to the number of children. Stress leads to health issues, and thus a decrease in fertility rate might explain an increase in quality in life expectancy. And I said that if this theory is correct, there should be a correlation between life expectancy and fertility rate. And that's true. And that's necessary, but not sufficient to confirm the theory, right? Because a relationship shown between two variables observed, collected, measured in an observational design does not allow inferences about causation, because we don't know, for instance, which one came first. Did fertility rate drop and that led to life expectancy increase? That kind of temporality needs to be present for a causal story to be told. Now, we need to be careful because this is an instance of something you probably have heard many, many times. Correlation is not causation, right? A correlation doesn't implicate causation. And one of the reasons for that, and I wanted to make that case here for you, one of the reasons for this, it's because you can have a third variable that is related to the two of them, and it makes this illusion of a correlation come through. Not that the correlation is not the illusion, but it may suggest a causal relationship that's not there. I'll give you one example that's kind of famous, that there is a very high correlation between eating the consumption of ice cream and crime rate. Consumption of ice cream being the explanatory variable and crime rate the response variable. Now, if there is a causal relationship, we could start an intervention in society for banning ice creams, right? Because, of course, if there's a causal relationship, what we should see is a reduction in crime rate. But, of course, this is super silly. And it would be very difficult to convince somebody that that correlation implicates some kind of causal effect. What is true is that there's a third variable there, lingering above that relationship, which is that during the summer, people eat more ice cream. And during the summer, people are more outside. And there are more opportunities for kind of disastrous encounters, basically, right? So it's the weather that explains higher crime rates. The fact that people are more outside is what explains it. The causal relationship is at that level. But because when the weather is hot, both ice cream consumption and crime rate go up, when you try and correlate these latter two variables, ice cream and crime rate, and that a relationship appears to be there. So you have to be careful. Third variables can be explaining this. And can you think about other reasons for this relationship to be there? We're going to explore one of them in our lab this week. Bye-bye. There will be one more video for introducing you guys to the lab. Really short one, like usual. Please watch it before you actually jump into the lab. All right? See you soon. Bye.